One thing we're going to be using today is a barometer. What are barometers used for? Yeah, measure the air pressure in this room. The air pressure is the weight of the atmosphere. And so basically the pressure in this room is atmospheric pressure, we call it. Atmospheric pressure is also known as, you know another name for atmospheric pressure? That's a unit of pressure, but it doesn't have to be atmospheric. That could be gas pressure, whatever. It's also known as the barometric pressure. I'll just call it PATM. So the barometric pressure and the atmospheric pressure are basically the same thing. How does a barometer work? The barometer works like this. Inside the barometer there's a tube. And this tube is pretty much upside down in a pool of liquid mercury. And so we have a situation like this. Okay. And let's say the mercury level is the same here, inside the tube and outside the tube. If the two liquid levels are the same, then that means whatever pressure we have inside here is equal to the pressure we have outside here. Okay, if there's an imbalance in pressure, then the liquid levels will change like a seesaw. Okay. Well, what is the pressure inside the tube? Do you know what the pressure inside the tube is? No, because this is what we call closed here. It might be atmospheric, but that's not how barometers are designed. The pressure inside the tube here is supposed to be, well, there's not supposed to be any gas in here. And so if there's no gas in here, are there any collisions? There are no collisions. If there are no collisions, then there is no pressure. In other words, if there's no gas, do you know what we call that? We call it a vacuum. And there are different levels of vacuum. For example, yesterday we saw high vacuum, ultra-high vacuum, etc. This should be what's called a perfect vacuum. A perfect vacuum has zero gas molecules. There's nothing in there. It's just empty space. Now, how do you get a perfect vacuum? Because getting an ultra-high vacuum is tough enough. It's extremely difficult. And so how do you get a perfect vacuum inside the tube? Well, you could try to put a pump there, but there's no pump that can really pump it out so easily. Right. What you do is you take the tube and you fill it up with mercury, and then you seal the mouth of the tube, flip it upside down, and put it into this pool of mercury. And that'll generate a vacuum. If the way we're going to get this perfect vacuum here is if we had a perfect vacuum in this room. Do you think that's possible? No, but if we did, if we had no gas outside and no gas inside, then what is the pressure? The pressure, and we have two types of pressure that we measure. We have something called the absolute pressure. The absolute pressure is 0 millimeters of mercury, 0 atmosphere, 0 whatever. And can you go below 0? No, that's impossible, because how can you get fewer than 0 molecules or 0 particles of gas in there? And so this is the absolute 0 pressure. But there's another type of pressure that sometimes we measure, and that's called gauge pressure. The gauge pressure is not going to be reading 0. Do you know what the gauge pressure would read? The gauge pressure would read minus 14.7 psi. That's what the gauge pressure would read, telling us we have 14.7 psi's worth of what we call vacuum. And so I want to talk just briefly about gauge pressure. And the origin of gauge pressure. Okay, let's say you had a helium tank, and this helium tank you're using to fill balloons. So there's a pressure gauge here, the tank of helium gas. And you fill balloons, and then pretty soon the tank goes empty. That is, you can't fill any more balloons with this helium tank. When you hit that point where the tank is empty, is the tank really empty? No. Because the tank still has some helium inside it. But the gauge is going to read 0. This is going to read 0 because now the pressure inside here is equal to the pressure outside here, and no helium is going to come out. The only way you can get the remaining helium out of here is to hook up a vacuum here and then suck the remaining helium out. If you could suck all the helium out so that it is truly empty, what would the gauge read? Negative 14.7, which that would be akin to absolute 0 in terms of pressure. Does that make sense? And so we have two. The problem is the units are the same, and so people just refer to it as gauge pressure or absolute pressure. You know, and that way they know. Because if somebody's talking about 14.7 psi, you know, are they talking about gauge or are they talking about absolute? And if you're talking about gauge, then you got to talk to other people about gauge and not mix them up. Otherwise, there's a problem. In fact, when we use cylinders of gas, we never let it go to 0 gauge pressure. Never. Do you know why? Because if you let it go to 0 gauge pressure, you get an extra charge. They charge you a lot of money. Do you know why they charge you a lot of money? Because if it goes to 0, then they think, wow, the valve was open. If the valve is open, well, helium has a very high diffusion rate, right? Helium can leak out of here. And then air can diffuse back in. And so what happens is helium leaks out, air leaks in. It doesn't even matter. It could have a slow diffusion rate. If the valve is open here, air is going to contaminate the cylinder. And when air contaminates the cylinder, the reason they charge you is because how do they clean it? How they clean this is they hook this up to a vacuum pump, pump down, backfill with pure helium, pump down, backfill with pure helium. They keep pumping down because they can't get a perfect vacuum. If they could get a perfect vacuum, then they could suck everything out of there, but they can't. And so they get let's say a high vacuum, and still there's air in there. They pump in pure helium, suck that out. And so by cycling it through like this, eventually it should be just pure helium left in there. But that's a huge waste of ultra pure helium, isn't it? And so that's why it's so expensive if you let the gauge pressure go to 0. But anyway, that's that. Normally we don't work in a vacuum, a pure vacuum. So what happens is there's air out here on the external surface of the mercury. And so if there's air out here, the air is going to generate a pressure, right? There are going to be collisions here. And so we get the air pressure, which is generated by the atmosphere, this blanket of air on top of us. So we got P atmosphere pushing down here. What's pushing down on the inside? What's pushing down on the inside is nothing. There's no gas on the inside. And so what that's going to do is it's going to push the liquid level up here. Like this. Since there's no gas here, when this stops rising, then what we'll do is we'll take a look at the level here and say this. The weight of the air will be equivalent to the weight of the liquid mercury. Well, the pressure of the liquid mercury we just get by the depth or the height. And so we just measure how tall this is, and that's going to be the atmospheric or the barometric pressure. The higher the atmospheric pressure, the taller this column is going to be. You know, the lower the atmospheric pressure, the lower the column is going to be. And so it's just the equal mass. And so this is what, 200,000 feet or whatever it was of air. This is going to be about 760 millimeters. If we made this out of water, do you know how tall it would be? It would be about 3 stories tall. And so what we have is we have a barometer mounted there next to the door. A little taller than 760. But if we filled it with water, it'd have to go through, and you'd have to climb upstairs to read it. Because water doesn't weigh much, right, compared to liquid mercury. Water is a lot less dense, and so you'd need a 3-story column to weigh the same amount as the air. So the reading here is going to be aided on our barometer by a little metal plate. And on the right side of the barometer, we'll have a knurled metal knob. If you twist this knob, what it does is it raises and lowers this metal plate that's mounted up here. And so what we want to do is get the bottom of the metal plate to line up with the top of the meniscus. The meniscus convex. So we'll just rotate this up or down. There's a white background to help you. You shouldn't see any white background here. So look for the white background to disappear and then stop there. And then we use this line here to measure the height of the column. And so we might see something like this. This might be the 760 mark here. They'll just call it 60. And then 761, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something like that. And so let's take the reading here. The meniscus lines up with what mark? So 761, 762, 763. So it's between 763 and 764. Normally what you do is you just guess. What does it look like? 763.5, 763.6. But we don't have to guess, because on the metal plate is a vernier scale. And what the vernier scale does is it just tells you what the guesstimated digit is, quite precisely. So there are going to be additional markings on the metal plate. For example, this would be the 0 line right here, right at the bottom of the plate. This would be 1, 2, 3, 4, 5, 6, 7, etc. Now, what you're looking for, actually, I didn't do 1, 2, 3, 4, 5. This would be 5 line. What you're looking for on the vernier scale, the vernier is going to give us the point X. And we want to see any of the lines on the metal plate that line up with any of the lines on the scale. And so if I look at the first line, this is the 0 line, it's mismatched. 1 is mismatched, 2 is mismatched, 3 is mismatched, 4 is mismatched, 5, 6 is matched. Do you see that? So the 6th line on the vernier scale matches with any line on the main scale here. And so that tells us that it's 0.6. And so this would be 763.6 millimeters of mercury. And that's because of this. Yeah. Is that clear? How to read that? Well, we have to talk about a couple of things that I'm oversimplifying. One is there really no gas in here? No. What gas might there be in here? Mercury vapor. Right, mercury is a liquid, and some of the mercury atoms can vaporize off the surface. And so we should correct for the mercury vapor that goes in here. But is mercury very volatile? No, volatile means it evaporates easily. It doesn't evaporate easily, so it's not that volatile. So we aren't going to worry about the little bit of mercury vapor that goes up in here. But the other thing we have to worry about, and this is more significant, is that mercury is a metal, and metals expand and contract with temperature. These barometers are calibrated at 0 degrees C, and so the lab here is like 22, 23 degrees C. It's a lot warmer than 0, so the mercury would have expanded a little bit. And so what we have on the barometer itself is a thermometer mounted to it so we can measure the temperature of the barometer. And so we need the temperature of the barometer as well as the pressure. And so this is what we call atmospheric pressure or barometric pressure. And we need the temperature of the barometer. When we measure the temperature of the barometer, it should be XX point X. So let's say the temperature of the barometer today was 22.3 degrees C. These are just made up numbers. You're going to record your own. Right? Now, the amount that the liquid mercury expands or contracts depends on temperature primarily, and secondarily it depends on the external pressure. If you have a lot of external pressure, then it might not expand as much, right? Or if you don't have much external pressure, it might expand more. And so it depends on how much pressure that mercury is under. And so we have the pressure here, we have the temperature here. Let's do the correction now for this. And so the barometer correction is going to change this reading. So we're going to call this the uncorrected barometric pressure, the pressure we just read right off the barometer. For the correction, we look at our chart. So we go to, on the top is the pressure, so 740 to 760. This is in torr. A torr and millimeter of mercury are it's the same thing. And so our pressure is bordered between 740 and 760. And our temperature is between 22 and 24. And so at 22 degrees C, what is the correction at 740 torr? 2.7? Okay, at 760, what is it? 2.7? Maybe I did the wrong one. It's all right. 2.7 and 2.7?
Yeah. If you do 2.4, it's 2.7.
This is, let me do something more. I picked the wrong number. Oh, I'm not at 740, sorry. I'm wrong. I'm above 760. Do you see that? And so I need to go out one more. So let me go out one more. Here to 780. What is it at 780 torr? 2.8. And then the next temperature we have is 24 degrees C. At 24 degrees C, what is it at 760? 3.0? And at 780, it's 3.1. Okay. Now, we don't have the right one because we're not at 22, we're at 22.3 degrees C. And we're not at 760, we're at 763.6 millimeters of mercury or torr. And so really what we need is we need the correction that's right here. What is the correction that's right there? Is it 2.7? Is it 2.8? What do you think it is? And so what we're going to do is we're going to do some linear interpolation. Have you done interpolations? The interpolation is, it's kind of like extrapolation, except we extrapolate between points. Therefore, it's called interpolation rather than extrapolation. Extrapolation would be beyond, after 2.8, what would it be? So, how do we do this? Okay, let's do the first one. It's pretty simple. We just take some ratios and figure out the distances. And so if from 22 to 22.3, we go 0.3 of the way. And from 22 to 24, that's 2. And so we want 0.3 out of 2. And so the first ratio would be over here, 0.3 out of 2. Will be equivalent to x. So x would be our 0.3, but the full distance here is only 0.3. So 0.3 over 2 is equal to x over 0.3. And then solve for x. X is going to equal 0.045. So this should equal 0.045. And we get the same ratio. So 0.3 over 2 ratio is the same as a 0.045 over 0.3 ratio. And so what that means is the point here, let's erase that. The point here will be 2.745. That would be here. Okay, now we need the same point here. And so this is going to be x, and the total distance here turns out to be the same. It's 0.3. So if that's the case, then this should be 2.845. So at 22.3 degrees C, the correction at 760 torr is 2.745. The correction at 780 torr is 2.845. All right, let me draw another table here. So let's redo this now. It's at 22.3, the correction at 760 is 2.745. The correction at 780 is 2.845. But we aren't at 760 and we aren't at 780. Where are we at? We're at 763. Or no, 763.6. Yeah, 763.6. So somewhere around here. And so what should the correction here be? So let's take a look at the ratios that we generate here. And so going from 760 to 763.6, we travel 3.6 out of the total distance of 20. And we want to do the same thing. What distance do we travel here, x, out of a total distance of, the difference here, 0.100? And so we'll set up the ratios. 3.6 out of 20 is equivalent to x out of 0.100. X is equal to Can somebody calculate it? 0.018. X is equal to 0.018.
Is it 0.18?
0.18?
I don't know.
Okay. Yeah, I think it's 0.018. So that means our corrected value here is going to be 0.018 on the way past 2.745. And so it'll be 2.763. So that means the correction at 22.3 degrees C and 763.6 torr, or millimeters of mercury, is 2.763. That means the mercury is expanded about 2.7 millimeters. And so we have to chop it off. Since our barometer reading is only to the nearest tenth, this is how we're going to calculate the corrected barometric pressure. The corrected barometric pressure is going to be our uncorrected, which is 763.6 millimeters of Hg minus the correction. The correction, we're just going to round it to to 1 decimal place, because we aren't allowed more than that. And so it comes out to 760.8 millimeters of Hg. This is what we call the corrected barometric pressure. Okay. Any questions with that? No? All right, barometers are used to measure atmospheric pressure, but what if you have a gas sample? Let's say you trap some gas in a container. How do you measure the pressure of a gas trapped in a container? Well, we use a different type of instrument for that. We use something called a manometer. And this particular manometer will be an open end. We're not going to talk about a closed end manometer, just an open end. In an open end manometer, we have a situation like this, where there's some kind of gas that's trapped here. And then we put in some liquid mercury here. This would be Hg liquid. The way it operates is like a seesaw. Here, do you see the two levels are uneven? If the two levels are even, then they have equal weight on both of them. But you can see that the right side is lower than the left side, which means the right side weighs more than the left side. Okay, so let's see what's pushing down on the right side. What's pushing down on the right side is the gas in here. And so we have the pressure of the gas sample. What's pushing down on the left side? Here. The air, the atmosphere. And so on this side, we have the pressure of the atmosphere. And in this case, the pressure of the atmosphere, the barometric pressure, is less than the pressure of the gas. The gas has got to weigh more. We can figure out what the pressure of the gas is by taking the lower level and then just setting it like this. So now if we imagine this is our seesaw and it's horizontal like this, then that means the weight on both sides is equal. And so what's pushing down on the right side is the gas, but now what's pushing down on the left side? You have the weight of the atmosphere plus the weight of the liquid mercury. And so if you measure the pressure of the atmosphere in millimeters of mercury using the barometer, and you measure the weight of the pressure of the liquid mercury just by its depth, you know, however millimeters this is, let's say this is 22 millimeters, then you have the 760 millimeters plus the 22 millimeters means you have a 780 millimeters worth of mercury pressure on the left. And so the pressure of the gas is equal to the pressure of the atmosphere plus the pressure of the liquid mercury here. And so all we do is we'll take a ruler and just measure how many millimeters. Normally the scale is mounted on here, so you can just count how many millimeters of mercury you have. And so this allows us to measure the pressure of a gas in a manometer. There are three scenarios that come up. One, when the gas pressure is greater than atmospheric. Two, when atmospheric pressure is greater than the gas pressure. And so let's take a look at that here. Okay, when atmospheric pressure is greater, then the liquid levels are going to look like this. And you can see that the atmospheric weighs more than the gas. So here I have my gas sample trapped. So I do the same thing. I put my seesaw horizontal like this and then see how much each side weighs. Doing that, I have the pressure of the atmosphere on the left. And so I'll just draw a line through the lower level here. And then on the right I have two things. I have the pressure of the gas inside the container plus the pressure of the liquid mercury, you know, however high this is, because we're at this depth of mercury. We aren't going deeper. We just stop here because this is how deep we need to go in the pool of mercury. And so what we end up with is, yes, P atmospheric is greater than P of the gas. And your book has a weird equation for this, which I don't really like. Your book says that if P atmospheric is greater than P of the gas, then you treat this as a positive depth. If P atmospheric, is less. If P atmospheric is greater than P of the gas, then you treat this as a negative depth. You know, I don't like that. Because the height is the height. You know, height's always going to be positive. And so I'd rather do it like this. We see that P atmospheric is equal to P of the gas plus P of the liquid mercury. And then we solve for the P of the gas. P of the gas is equal to P of the atmospheric minus P of the mercury liquid. Okay, so again, what your book does is your book calls one of these heights negative, like negative 22 millimeters, and the other height positive, positive 22 millimeters, depending on which side it's on. But it's a hassle. I don't bother with that. We just do the green, set the levels equal, and then figure it out from there. All right, the last possibility for the manometer is this. It's when the gas pressure is equal to atmospheric pressure. What is it going to look like? Yeah, they're going to be at the same level. Right. So let's go ahead and draw that out. So we trap a gas sample in here, and this scenario is the pressure of the atmosphere, or barometric pressure, is the same as the gas pressure, and we know that because the levels are equal. So P of the gas is equal to P the atmosphere. So, what are we doing today in lab? Yeah. So we have an unknown sample. We're going to get it. Don't use all of it. Use how much? 1.5 grams, and don't go over 1.5 grams. If you go over 1.5 grams, you run the risk of generating too much gas, more gas than the apparatus can handle, and you have to start over. It's not such a big deal starting over because this experiment doesn't take that much time. And so today somebody did it 3 times because stuff happened. So sometimes the tube popped out or the stopper popped off and different things happened. Okay. So we get a sample like this, and we need to weigh it. And so typically what you do is, rather than using copper wire like they suggest, I would just get a beaker and tare it. Actually, you know what I'd like to do is I'd like to get a beaker and the test tube and tare it, and then tap the sample into the test tube. But for this lab, we need to know, do we need to know how much the test tube weighs?
Yes.
Yes. And so get a beaker, tare it, put it in the test tube, weigh it. And then tap in about 1.5 grams of sample, weigh it. And then tap in, what else are we going to use? Manganese fluoroxide or manganese dioxide catalyst. Do we have to be precise in the amount of catalyst we put in there? No, not at all. You just put a little scoop in there. A scoop would be like a match head's worth. We don't need much catalyst in here. If you overshoot or undershoot, no big deal. But what we do need to know is how much it weighs. And so we need to know how much everything weighs in this, except for the beaker. And so keep track of everything. And so we weigh those out. I don't have any catalyst in here. If I don't have any catalyst, what's going to happen? It's going to take longer. Right? What catalysts do is they speed up the reaction. But it's okay. We'll take a little more time. All right, these utility clamps, you can adjust the angle by releasing the lock nut here. Get it at what angle? 30 degrees. I do 45 or so. 30 is a little, something like that. 30 to 45 degrees. And then clamp it. Do I want to clamp it here?
No.
I don't want to clamp it here because you're going to start burning the rubber on the utility clamp and stink up the lab. And so clamp it all the way at the top or the mouth of the test tube here. Now we're good. So here's my sample here. All right, now I need to set up the gas trap because we're going to generate oxygen gas and I want to make sure I trap all of it. I'm going to use DI water for this. I don't like to use tap water. No. You're going to use tap water whether you like it or not. But if the DI water were working, you'd use DI water. You fill up the Florence flask full, and this goes in here. That. And then we have a beaker. How many mils does it say to put in the beaker? 100 is too little. Yeah, I'd go with 200. 200 because, you know, with 100, the depth of water here is so shallow that the tube might pop up a little bit and suck in air. If that happens, you got to do it over again. Okay, now what I want to do is I want to connect, what I want to do is I want to purge the air out of the tube and connect these two containers of water with a tube of water. Somebody, I gave my pipette bulb to somebody. I have another one here. We're not going to blow this. We're just going to use a pipette bulb and just squeeze it. This. And so here I go. I'm going to squeeze this to squeeze the air out of here. Let's see. It's too much pressure. That's why these have to be secure. Otherwise, if that pops off during the experiment, then you're doing run 2. Which has already happened today. Okay, I need to do this with... Okay. So what we want to do is we want to get the air out, and you can see if we got all the air out by siphoning water back and forth. If it doesn't siphon back and forth, then we know maybe we didn't get all the air out. Do you see?
Yeah.
If I can siphon? Okay, so I filled up the Florence flask. Let's go ahead and drain the Florence flask. Fill up the beaker, and make sure that there are no pockets of air in there. And it looks like I got it all out. Right? And so this looks good. Okay, now the thing is I want to back siphon water into the Florence flask. I want my Florence flask to be full, but I want the liquid level below the stopper. So stop about it like a ½ centimeter below or around there. And so I'll just hold this here. When the two liquid levels are equal, then it'll stop. So let's see. Okay, that should be good. Full enough, right? Leave a little air gap there. You see that? I'll keep the levels equal so it doesn't screw up anything. Now what you need to do is you need to seal the air inside here. And so I'm going to seal this tight here. Now look at, I have a manometer. Here's my gas sample here, right? What's pushing down on this liquid level here? Atmosphere. What's pushing down on this liquid level here? The trapped air, right? Is the trapped air inside here the same pressure as atmosphere out here? No. What's at a higher pressure? The air inside here or the atmosphere? The air inside here. How do I know? Because of the liquid level. The air liquid level is down here. The atmosphere is up here. That means atmospheric pressure is lower than the gas pressure here. How can I fix that? Well, this is the way I'm going to fix it. I'm going to fix it by back siphoning water into the beaker, like this. When I back siphon water into the beaker, what that's going to do is water is going to get sucked from the Florence flask into the beaker, creating a slight vacuum here, which is going to release some of the pressure on the air. And so now what is it? Is the air pressure higher or lower now than atmospheric, the air pressure inside the trapped air? What's at a higher pressure now? Atmospheric. The barometric pressure is higher. How do I know? Because the liquid level. And so what I have to do is I just have to siphon just the right amount of water. How do I just siphon the right amount of water? I hold this. You know, if I go this way, look at the water level inside the flask. Do you see I can lower it? And that's changing the pressure of the gas inside there. And so what I want to do is I want to make sure that the pressure of the trapped air in here is exactly the same as atmospheric. So what I'll do is I'll set this down, get the liquid levels to be exactly equal, and that's siphon just the right amount of water into the beaker or out of the beaker, and then I'm going to pinch the hose. Now I know that the air that's in here is at atmospheric pressure, and I'm going to dump this water here. And then I'm going to replace the tube back in here. I'll probably jam this in here so it doesn't pop out. Okay, now we're set. So I'll go ahead and start the reaction. Lab coat. Do you guys know what a proper flame looks like? You know about the cone? Okay, good. So you don't heat it at the hot part. What's the hottest part of the flame? At the tip of the cone. Don't heat it at the tip of the cone yet. You know, because this, especially with a catalyst, this reaction can get going quite vigorously, generate too much pressure, and pop the stoppers off, making it repeat it. And so heat it on the soft part of the flame first. Once it starts going and it looks controlled, then start heating it on the hard part of the flame. Okay, this is without catalyst. My KClO3 is starting to melt. Remember, KClO3 doesn't have such a high melting point. Pretty easy stuff to melt. Let's watch what happens here to this. Do you see what's happening in the beaker? Yeah, water is being forced into the beaker. It looks like my KClO3 is boiling, but what it is we're generating lots of O2 gas. And so we aren't vaporizing the KClO3. How do I know it's done? Is this done? No, I mean, there's a lot of gas still being generated. People always ask me, how many more minutes do I need to eat? I don't know. You just keep heating it until, it depends on the temperature of the flame, you know. You keep heating it until, gas stops forming and you're heating it and nothing's happening. Nothing's been happening for the last few minutes. If nothing's been happening for the last few minutes, then you're done. You're done. And so what happened here is we're capturing the oxygen gas by water displacement. And so take a look now. You know, this Florence flask was full, but now we generated a whole bunch of oxygen gas, right? And now it's trapped. And so in this, we have air and oxygen gas trapped here, right? Okay. Well, oops. Don't want that to pop off. If it's not popped off, then it's a repeat. So, you know, some people clamp this on here with a test tube clamp. All right, now what we got to figure out is how much oxygen gas did we just generate? And so let's talk about that. In order to figure out how many moles of oxygen gas generated, what do we need to know?
Water was displaced.
Yeah. Well, we'll need to know the volume of oxygen gas, right? And so we'll have to figure out, well, the volume's easy because the volume should be the amount of water displaced, right? But we'll come back to the volume again. We need to know the pressure of the oxygen gas, and we need to know the temperature of the oxygen gas. But there's a problem. The problem is this. One, there was air in here. Do we have to worry about the air that was in here before? No, we shouldn't, because the volume of water should be just only the volume of oxygen gas generated. It's the volume of oxygen gas generated. In other words, volumes are additive. That is, the volume of A plus the volume of B equals V total when we're under conditions of Avogadro's law or under conditions of Dalton's? Under conditions of Avogadro's. Avogadro's means what? Remember, the volumes add up as long as the pressure stays the same. So we got to make sure that the pressure didn't change. Did the pressure change?
Did the pressure change? Yes. Look at the liquid levels. Are the liquid levels the same? Is the pressure of the trapped gases in there the same as the pressure outside? No, it's not. And so how do I get the pressures to match? I siphon water one way or the other until the liquid levels are the same. And so it's easy. I just raise this up until the liquid levels are the same. The water will siphon one way or the other, and now I know the pressures are the same because I just raise this up. One of them, either the beaker or the flask, you raise that up, and now it's the same. I'm going to pinch this so water can't siphon back and forth, right? Because I don't want this volume to change. This is the volume of gas I just generated, the volume of oxygen gas at what pressure? At what pressure? Atmospheric pressure. Does that make sense? Okay, so now I can take one of those large grad cylinders and measure the volume of this water. The volume of this water should be the volume of the oxygen gas I just trapped, right? And the pressure of this should be the pressure of the oxygen should be, well, now we got to think. Actually, it's even more complicated. Do you know I didn't generate pure oxygen gas? Okay, now I'm going to forget about the air because do we have to worry about the air? No. But, I didn't generate. This is not pure oxygen gas that I generated. Do you know why? Because the oxygen was bubbled through water. Whenever you bubble a gas through water, what happens is it becomes saturated with water vapor. In other words, it becomes 100% relative humidity. And so what that means is that I have a mixture. It's a mixture of oxygen and water vapor. It's like, if you go to the indoor pool over here, it's so humid in there. Have you walked in that room? Yeah, it's completely sealed and the humidity is way up. But if you took all the air in this room and bubbled it through a pool of water and then just brought it back in the room, it would feel awful in here because it would be very, very humid, right? And so that's the same thing. This oxygen gas is extremely humid right now because it's saturated with water vapor. And so when it's saturated, we don't call it O2, we call it wet O2. And the pressure is the pressure of the wet O2, and the temperature is not the temperature of pure O2, it's the temperature of wet O2. Wet O2 is a mixture. It's a mixture of water vapor and oxygen. So what should we do? Let's see. The volume of wet O2 is equal to the volume of dry O2 plus the volume of water vapor. True or false? Sure? The pressure of wet O2 is equal to the pressure of dry O2 plus the pressure of water vapor. True or false? False? True? The temperature of wet O2 is equal to the temperature of dry O2 plus the temperature of water vapor? True or false? False. This is obviously false. The temperature of the O2 is going to be the same as the temperature of the water vapor, right? They're at the same temperature. So the temperature of wet O2, that's easy, is equal to the temperature of the dry O2. Because the water vapor and the oxygen are going to be at the same temperature in this gas mixture. Would you agree? Yeah. It's like the nitrogen and oxygen in this room. The nitrogen and the oxygen are at the exact same temperature. They have the exact same kinetic energy, right? So which one of these is true? Or are both these true? Can both of these be true at the same time?
No.
No. And so how do we handle this gas mixture? Well, I know what we did with the air. With the air is the volume of air plus the volume of O2 is now the total volume. That is Avogadro's, right? And so the volumes were additive. Any volume that I added to this trapped air is just pure O2. It's Avogadro's law. What should we do about the water? Well, either we could use this one or this one, right? But both can't be true at the same time. And so what do you want to do? Do you want to take this volume here and say, okay, how much of this volume is from the O2 and how much of this volume is from water vapor? And therefore we can figure it out, because now I have 250 milliliters. If I have 250 milliliters and maybe 25 milliliters was from the water vapor, then that means I only have 225 milliliters of O2 generated, not 250 milliliters of O2. Does that make sense? But the problem is, I don't know how many milliliters of water vapor I just generated. That's very difficult. Very difficult. But I do know this. I do know that the pressure of water vapor generated depends only on the temperature for 100% humidity. And so what happens is the humidity climbs and climbs and climbs and then stops once it hits a certain pressure that's dictated by the temperature. I can find this in the table. And so what I need to do is I need to get the temperature of the water vapor. Well, do you think the temperature of the gas in here is the same as the temperature of the barometer? No. And so what I'm going to do is I'm going to pop the stopper off here and then place a thermometer in the gas sample here and measure its temperature. When I get the temperature of the gas, then I'm going to go to something called a water vapor pressure table, and then look. Let's say the temperature of the water vapor were 24.5 degrees C. If this were 24.5 degrees C, then I just do linear interpolation. I have the water vapor pressure at 24, I have the vapor pressure at 25, so 24.5 is halfway between, so that means the vapor pressure must be halfway between the two entries here. Does that make sense? And so we do another linear interpolation to figure out what the vapor pressure of the water is. Once we know the vapor pressure of the water, then we can calculate the pressure of the O2. The pressure of the O2 is going to equal the pressure of the wet O2 minus the pressure of the water vapor. What is the pressure of the wet O2? The pressure of the wet O2 is the same as, remember we equalize the pressure, so it's the same as atmospheric pressure. What is the volume of wet O2? Well, this is Dalton's law. Dalton's law says that volume is constant. Therefore, the volume of wet O2 is the same as the volume of dry O2, which is the same as the volume of water vapor. Right? All the volumes are the same. All right, so now we have all the data. We have the volume of dry O2, we have the pressure of dry O2, and the temperature of dry O2. What can we calculate? We can calculate the moles of pure O2. And so I'm going to call this calculation B. We want the percent KClO3 in this unknown, and that depends on how many grams of KClO3 we have in X grams of unknown. And so we do the mass of KClO3 over the mass of the unknown times 100%. The mass of the KClO3, this is how we're going to get it. We're going to figure out the moles of O2. The moles of O2 is just equal to the pressure of O2 times the volume of O2 times our temperature of O2. Okay, once we have the moles of O2, then we're going to convert that into moles of KClO3 using the mole ratio.
So mole-to-mole conversion, and then once we have moles of KClO3, we'll go to mass of KClO3 using the molar mass. And then we're done. Uh-huh.
I'm sorry, I missed what you were saying about the very first equation. You said it's moles of O2 is equal. So that's the ideal gas law, right?
Yeah, ideal gas law. We'll use the ideal gas law here. And then we'll use the balanced chemical equation to do mole-to-mole conversion, stoichiometry conversion. Okay, then we'll figure out how much, what the percent KClO3 is. It turns out there's a much easier way to do this. A much easier way to do this is we'll call calculation A. With calculation A, you know what? We don't throw away this yet. You know what we're going to do with this? The residue? We're going to weigh it. And so we're going to weigh the remaining solid here. Why are we going to weigh the remaining solid? Yeah. So basically this redox decomposition decomposes into KCl and O2. And so this will be the initial mass. Actually, I should say plus, catalyst. This would be plus catalyst. So initial mass, and then this would be the residue mass, or the final mass. Just the solid residue. The O2 is escaped. So if we take the initial mass here minus the solid residue mass, what's missing? The O2. And so we'll end up with a mass of O2. There's the only thing that's left, the solid phase. This is solid. This is solid. Is the O2 gas. Escape. Conservation of mass. So what we'll do here is we'll go from mass of O2 to moles of O2, from moles of O2 to moles of KClO3, moles of KClO3 to mass of KClO3, and then we'll calculate it. The percent KClO3 is just equal to the mass of KClO3 divided by the mass of unknown times 100%. Calculation A and calculation B should yield the exact same percentage. However, which one do you think will be more accurate? Calculation A. Just a lot fewer measurements and not difficult. The way these samples is very easy. And so B is going to be, a lot more uncertainty in there because all that pressure equalizing and all this volume and whatever else measurement isn't so precise. All right, any questions on this? No. Okay, you're going to work in pairs for this lab.